Hello, this is Math 2-115 coming to you from the College of DuPage, and this is a continuation of the lecture entitled The Logic of Quantified Statements. When last we left off, you were working on this problem. Maybe you finished it, maybe you didn't, but you were to write a statement formally using these symbols, and the statement you were trying to write formally was, there is a smallest positive integer. Maybe you did it already, but if not, I'll give you some time now. You know what to do. Let's see how you did. And you should have written, there exists a positive integer m such that for every positive integer n, m is less than or equal to n. And number 1 is the number that satisfies that. The same kind of question here, I'm asking you to consider the statement there's no smallest positive real number, and that's true because a positive real number is going to be on this side. If you pick one that's x over 2 is always going to be less than, closer to the 0. So it is true, but I want you to take this statement, there is no smallest positive real number, and write it formally using these symbols. For every n, there exists. You know what to do. Let's see how you did. And you should have come with, for every positive real number x, comma, there exists a positive real number y such that y is less than x. We're writing this without negatives, and so there are other things you could have written, but this is the cleanest and what you really should say. The definition of a sequence that's studied in calculus uses both quantifiers, for every n there exists, and also if then. It really is pretty complicated. Symbolically, this is what it says. For every epsilon greater than 0, there exists an integer capital N such that for every integer lowercase n, if lowercase n is bigger than capital N, then L minus epsilon is less than, A sub n is less than L plus epsilon. Considering the logical complexity of this definition, it's no wonder that many students find it hard to understand. You also must be careful about ambiguity. This picture shows some visual ambiguity. Depending on how you're looking at it, you might look at this picture and see a woman that's looking into the computer screen, and this would be her necklace, and that's the woman that's looking that way. You might see also, though, if you look at it in a different way, that this is not the woman's jawbone, but this is the nose of someone who's looking out more or less towards you out of the computer screen. Instead of this being a necklace, this is the mouth. Now, these are clever pictures, but ambiguity can exist in words. People can say something and you don't really know what they mean. But you cannot have that happening in formal language because you're programming things using the formal language, and so the interpretation has to be rigorous or else your program is not going to work. Let's move on and talk about negations of statements with more than one quantifier. You can use the same rules to negate statements with several quantifiers that you use to negate simpler quantified statements. So if you take the negation of this statement, that's logically equivalent to there exists x in d such that not p of x. And if you negate this statement, that is logically equivalent to for every x in d, not p of x. So if you negate this statement that has for every n there exists in it, this will be logically equivalent to, after you do some simplification, and we do two stages, first this stage and then this stage, there exists an x in d such that for every y in e, not p of xy, and similarly for this. So you want to be careful of about this. And this summarizes that statement. This is how you handle that. The negation of this statement is logically equivalent to this statement, and the negation of this statement is logically equivalent to this statement. Think about it a bit. Let's do an example now. This is the Tarski's World situation. So when you're answering these questions or studying these questions, you look at this as being the entire universe. And what you're supposed to do here is write a negation for each of the following statements and use Tarski's world to determine which is true, the given statement or its negative. And so you have 2 to do here. For every square x, there's a circle y such that x and y have the same color. And the second one is there's a triangle x such that for every square y, x is to the right of y. You know what to do. Let's see how you did. Okay, so the negation is the first negation of the statement is going to be written this way. There exists a square x such that there does not exist a square y such that x and y have the same color. But then you expand this and you change the exists to a for every and do not have the same color. So this is going to be there exists a square x such that for every circle y, x and y do not have the same color. The negation is true. Square E is black, and no circle in this world is black. So therefore, there is a square that does not have the same color as any circle. The second one, you again do it step by step, but the final version of the negation should be, for every triangle x, there exists a square y such that x is not to the right of y. This is true because no matter what triangle is chosen, it is not to the right of square G or square J, which are the only squares in this world. You may ask, gee, does it make a difference whether I have for every first or there exists first? And so we're going to explore that here. We're going to again look at Tarski's world, the same picture you've been looking at. Do the following 2 statements have the same truth value? For every square x, there is a triangle y such that x and y have different colors. And B, there exists a triangle y such that for every square x, x and y have different colors. Think through this and we'll talk about it in a moment. You know what to do. Let's see how you did. Okay, so statement A says that if someone gives you one of the squares, you can find a triangle with a different color. This is true. Statement B says there is one particular triangle in Tarski's world that has different colors from every one of the squares in the world. This is false. 2 of the triangles are gray, but they cannot be used to show the truth of the statement because Tarski's world contains gray squares. The only other triangle is black, but it cannot be used either because there is a black square. Thus, one of the statements is true and the other one is false. They have opposite truth values. And that means you have to be careful. If a statement contains 2 different quantifiers, reversing their order may change the truth value of the statement to its opposite. We're staying with Tarski's world. So here you have several things you're being asked to do. You're supposed to use formal logic notation to write each of the following statements, and also write a formal negation for each of the statements, and there's 4 of them. 1, 2, 3, 4. You know what to do. Let's see how you did. Okay, so the statement is for every x, circle x implies above x, comma, f. And so the negation of that, after you simplify it, is there exists x, a circle, and it is not above f. In B, the statement is there exists an x such that, and then it is square x, it's a black square basically. What happens here is when you negate that statement, after you simplify it and use your rules of logic, it is for every x, negation square x or negation x. And notice that here we're using De Morgan's law that we studied earlier. In C, the statement was for every x, circle x implies there exists a y such that y is a square and the same color. as x. The negation of that, and there's a lot of simplification happening here, is, again, in the final step list De Morgan's law, there exists a circle x set and for every y. The negation, it's not a square, and it is not the same color as x. The last one is, this is what you should have come up with, and the negation, when you simplify it, is shown here. Spend some time with this. These things are not simple, I think. The disadvantage of fully formal notation is that because it is complex and somewhat remote from intuitive understanding when we use it, we may make errors that go unrecognized. You can write a program that the program will do exactly what you tell it to, but you told it to do the wrong thing. The advantage, however, is that operations such as taking negations can be completely mechanical and programmed on a computer. Also, when we become comfortable with formal manipulations, we can use them to check our intuition, and then we can use our intuition to check our formal manipulations. Formal logic notation is used in computer science, such as artificial intelligence, program verification, that's proving the program really works, automata theory, and formal languages. Taken together, these symbols are called the language of first order logic, and you might say it's simpler than most foreign languages, but it is a foreign language, and so you need to understand it. There is a programming language called Prolog, that is short for programming in logic, that was developed in the 70s by these programmers, and it's useful in artificial intelligence. And a simple program consists of a set of statements describing a situation with some questions, and built in are search and inference techniques needed to answer the questions by deriving answers from the given statement. This frees the programmer from the necessity of having to write separate programs to answer each type of question. This is actually used in math programs and many things these days. Here's a very simple Prolog formula. So consider this picture. You've got blocks stacked, and they're colored, and some of them are colored blue, and some of them are colored gray, and some of them are numbered. Okay, so here are some statements in Prolog that describe the picture and ask questions. Now the two questions are asked down here, okay, but it starts out saying some things. It tells you things about the blocks, and it also tells you relationships. For example, this says that the gray block in the first stack is above the blue block, and this tells you what those things mean, and so on and so forth. And so that's and these are, you know, the definitions, and these are the questions that you're trying to ask. And so this talks about how they're interpreted. The statement is above xy if is above xy and is above yz. That's saying if the first is above the second and the first is above, excuse me, let me do it this way. If this one is above this one and the second one is above the third, then that means the first is above the third. That's a logical inference statement. And so we have this, and so when you're answering the question, if you think about this, you ask the first question, ask whether B1 is colored blue, and if you put it into the program, it will answer yes. Statement 2, ask is if x is above w. Now what that says, x, for which blocks x is x above w, and it will come back and give you two answers. Prolog finds the first solution by merely searching the original set for the facts, but it must infer the second one from this inference statement down here. So just to get a little bit of experience for this, I'm going to ask you to consider this picture, and it's the same program, but you want to write the answers that Prolog would give to these questions if we added them to the program. So is B2 above W1? Is W1 above X? or what color is the things that are above x, and what color is, what do we get for x is blue. So give it a go, and you're answering the question based on this diagram. And so the answer to the first one should be no, because the question was, is B2 above W1? It's not. If you look at the picture, B2 is not above W1. It's in a totally different stack. The question, for what colors is X the predicate? W1 is colored X true, and that's when X is white. And the question, the last one means, for what blocks is the predicate X is colored blue true? And the answers are X is equal to B1, B2, and B3. We'll continue this later. This quantification is kind of a long topic.